Hi guys, today we'll be looking into kernel timers. So kernel timers, they are used to schedule execution of a function at a particular time in the near future. So usages are like which are used in Linux kernel are implementation of timeouts. So schedule underscore timeout, it internally uses kernel timers. TCP protocol, it uses kernel timers for wait timeouts. So timer is very easy to use. You have to perform these following steps. So you have to first initialize the timer. After initialization, you have to specify an expiration time. Then you have to also specify a function that should execute when the timer expires upon expiration. And then you have to activate the timer. So this is how it works. It's very easy for you. You have to follow these 4 steps. First, you initialize the timer. You specify an expiration time. Then you specify a function which should execute on expiration and then activate the timer. So the function will execute whenever the timer expires. The important point here is timers are not cyclic. The timer is destroyed after it expires. So in current Linux kernel, there are 2 types of timers. One is low resolution timer, the other is high resolution timer. In this session, we'll be looking into low resolution timer. Next session, we'll be looking into high resolution timer. So low resolution timers, they are organized on lists. So it is HList underscore node. So this is a data structure which represents a timer is timer underscore list. The header file for this is linux timer.h. The implementation for this is present in kernel timer.c file. So you can see it's very easy structure. There's a function field which saves a pointer to a callback function which will be invoked upon timeout. Then we have expires field which specifies the time in jiffys at which the timer expires. So and then we have flags, and this is a linked list. It's a list, not a linked list. It's a list. So what are the use cases in Linux kernel which this particular low resolution timer is used is? So they're used to detect when a device or a network peer has failed to respond within the expected time. Suppose if the response happens, then the timer is cancelled. So if the response happens, then the code will cancel the timer. But if there is no response, then the error is sent back to the application layer. So it is used to detect whether the network peer or device has failed to respond within the expected time. This is one of the use case in Linux kernel. So there are many use cases. As we said, schedule underscore timeout. It also uses kernel timers, low resolution kernel timers. So initialization of this particular structure, there are again 2 ways. One is a static way, the other is a dynamic way. In static way, you use define underscore timer, you specify a name of the timer, struct timer underscore list, you specify the function name. Then you have timer underscore setup. This is a dynamic way. If you have allocated memory using kmalog, you can specify it. You also need to specify the function and the flags. So here you need, additionally, you need to specify the flags, whereas in define static way, you are not going to specify flags. So let's see an example of this. So static timer, static initialization. So define underscore timer. I have included timer.h header file. Define underscore timer, the name of the variable structure, the function which you want to execute. So this is the prototype of the function. It returns void, does not return anything, and it accepts an argument which is of type struct timer underscore list. So what I'm doing is in my init function, I'm printing the value of expires. What is the value of expires? I'm only initializing the timer here. I'm not setting any expiration time. I'm only initializing the timer and specifying the function which should execute on the expiration of timer. So let's see what will be the output for this. So expires is 0. So this means we have not set the expiration time. Hence, the function which we have initialized or specified will not be executed. So we have to specify the expiration time. So how can I specify the expiration time? So to specify the expiration time, we have a function known as mod underscore timer. So mod underscore timer or modify timer, you can say. It takes an argument, two arguments. One is the timer underscore list, which is the kernel timer, and then the expiry. This is the value which you have to specify in jiffies. And at this particular jiffies, the timer is expected to run, and the function which you have specified will execute. So let's actually specify an expiration time now. So I'm saying now here jiffies plus 1000. So whatever the current jiffies I have plus 1000 jiffies. So at that time, please run my timer function. So I'm also printing jiffies value here, the timer function. So also I print the value of expires after a run mod underscore timer. So this should update the expire field in the timer structure. When I say mod underscore timer, it should update the expires field in the structure. So let's see the output now. So you can see when I executed mod underscore timer, it has set the expires field, and after the 1000 seconds, 1000 jiffies, it has actually called our timer function, and you can see here it's the same because we have read jiffies after the function executed. There is one jiffy incremented there. So you can see here the timer function has been executed at this particular jiffies. So this is how kernel timers works. Very simple. You initialize the timer with this function which you want to execute on expiration, and then you have to specify the expiration time. And that's it. So the kernel runs the timer handler when the current tick count, or you can say jiffies, is equal to or greater than the specified expiration. Although the kernel guarantees to run no timer handler prior to the timer's expiration. So kernel guarantees that timer handler will not run before the timer's expiration, but there may be a delay in running the timer. So after the expiration, there can be a delay, but the timer handler will not be executed prior to the timer's expiration. This is guaranteed by the kernel. So we have already seen this. We can convert jiffies to seconds or nanoseconds. We have structures like time val and time spec. Time val is of microsecond resolution. Time spec is of nanosecond resolution. We have seen this in our recent session. So we can use this here in kernel timers. If I want my kernel timer to execute after 10 seconds, I can use a time spec, and I can set the second field to Z10. And in the expiration, I can use current jiffies plus I can convert this 10 second to jiffies. Or I can use milliseconds to jiffies also here. So there are many ways to convert it to jiffies. So time spec to jiffies will convert this particular 10 seconds to jiffies, and it will update the expiration time. And after 10 seconds, this particular function will execute. So let's run this code. So it is now 7685. So we have to wait. And after 10 seconds, you can see the timer function has been executed. So question for you. Guess in which context timer handler runs. Whether it runs in process context or whether it runs in interrupt context. So for understanding this, you have to understand who actually calls the timer handler. Who is calling this timer handler? That will make you know, like that will give you a hint whether it runs in an interrupt context or it runs in an process context. So for this, let's run a code which we will be using our in underscore interrupt macro, which will give us whether we are running in an interrupt context or whether we are running in a process context. So this is the function which tells that. I call this function from the timer handler print underscore context. Again, the code is same. It executes the function timer handler after 10 seconds. So let me modify, let's say I want to execute this after 5 seconds. So now the timer handler will be executed after 5 seconds. So let's compile this and load this module. So after 5 seconds, our timer handler will be executed, and you can see it is running in interrupt context and not in the process context. So your kernel timer is running in interrupt context, not in process context. This is because the timer handlers are being called from timer interrupts by soft IRQs. So we'll be seeing that. So timer implementation, how it works. Kernel executes timers in bottom half context as soft IRQs after the timer interrupt completes. So after the timer interrupt completes, timer interrupt handler, it runs a function known as update underscore process underscore time, which calls run underscore local underscore timers function. You can see this is a function which is present. This function is raising a soft IRQ, which is timer underscore soft IRQ. So for each and every timer interrupt, this particular soft IRQ will be raised, and this particular is being handled. This particular soft IRQ is being handled by this function run underscore timer underscore soft IRQ. This function will check if there are any expired timers on the current processor, and then it executes it. So this is how it works. This is the reason it runs in interrupt context, not in process context, because it is being executed by soft IRQs. So we can verify that who is executing what by calling dump underscore stack. Dump underscore stack will give us the whole call trace of the function, this particular function, timer underscore function. So let's actually execute this and see the output. So this is a 10-second delay. The expiration time is set to 10 seconds. So after 10 seconds, we'll be seeing the stack dump. So you can see there's a timer interrupt. And then after timer interrupt has been completed, you have soft IRQ. And it runs a function run underscore timer underscore soft IRQ, which is what we have discussed. And finally, it calls our timer function, which is calling dump underscore stack. So you can see here, this is how our particular timer underscore function or the timer handler is being executed on timer interrupt. This is the reason why it executes in interrupt context. So are interrupts disabled while running timer handler? So this is very easy question now. You already know about soft IRQs, but the soft IRQs run with interrupt enabled or disabled. Simple question for you now. If you know how soft IRQs work, which we have already discussed, this will be an easy answer for you. So we can verify that by using macro IRQS underscore disabled. This will tell us whether the interrupts are enabled or disabled on the local processor. So IRQS underscore disabled will tell us whether interrupts are enabled or disabled only on the local processor. So I call this particular function from my timer handler, which will tell whether my interrupts are enabled or disabled when the timer handler runs. So again, there's a 10-second delay for this because the expiration time is set for 10 seconds. And you can see here, Kernel timers, they run with in interrupt context with interrupts enabled. This is because soft hierarchies run in interrupt context with interrupts enabled. And very easy question again, whether this is running in a hard hierarchy context or not soft hierarchy context. Very simple question. If you know about soft hierarchies, you can easily answer this. So I'm calling this print underscore context, which is actually calling in underscore hierarchy, which will tell me whether it is running in hard hierarchy context or not. So let's run this code. So it is not running in hard hierarchy context, it is running in soft IRQ context. So this will now tell us whether this is running in soft IRQ or hard IRQ. In underscore soft IRQ will tell whether the context is soft IRQ or not. Again, I'm running this from my timer function. I'm calling this function, and the expiration time is set to 10 seconds. Let's modify to 3 seconds or something. So it's running in soft hierarchy context, and it is not running in hard hierarchy context. So the question for you now is whether kernel checks all the timer entries in linked list on each race soft hierarchy. So we know after timer interrupts, it raises a soft hierarchy, timer underscore soft hierarchy, and the soft hierarchy function, which is a registered, will be executed. Now the question here is whether all the timer entries which are present in a linked list are being checked by the kernel for each raised soft hierarchy. What do you think? So this is the answer. Kernel, it partitions timers into 5 groups based on their expiration value. Timers move down through the groups as their expiration time draws closer. So it moves in between groups whenever it decides based on the expiration time. So this partitioning ensures that most execution of the timer soft IRQ kernel has to do little work to find the expired time. So kernel actually maintains partitions, 5 partitions based on the expiration value, and kernel will only check the first partition which has the expiration time very less. So this is how it works. So it does not check all the entries present in the timer list. It only checks the few entries in the first partition basically, which is having a minimum expiration time. So delete underscore timer, this function deactivates a timer. So you have a started a timer. Now you want to remove the module. What happens if you do not delete the timer? This is a problem, right? So delete underscore timer, the function returns whether it has activated a pending timer or not. So let's see what happens if I do not call delete underscore timer and instead I remove the module. So I have already a modules here which has a 10-second of expiration time. See, see what happens because if you do not delete the timer and we remove the module. So I'm loading this module and I instantly remove the module now. So I have instantly removed the module. Now after 10 seconds, this will, you can see here, my CPU has been reset because of this. Because of this, the CPU has been reset because we have removed the module without actually cleaning up, without actually calling del underscore timer. Let me restart my machine. So I have restarted my machine. So we came to know in our previous example that we have to clean up, we have to remove, we have to call delete underscore timer in our exit function, which deactivates the timer. Otherwise, the system will be corrupt, kernel will corrupt, and you have to restart your machine. So delete underscore timer, this function returns whether it has deactivated a pending timer or not. So it actually deactivates a timer, and then it returns whether it has deactivated a pending timer or not. So delete underscore timer of an inactive timer, which is already completed, it returns 0. Delete underscore timer of an active timer, it returns 1. So let's try this out. So the same code in my exit function, in my module exit function, I'm calling delete underscore timer. So this function will deactivate a timer, and it returns 0 or 1 depending on whether the timer is active or inactive. So timer is active now. So let's remove the module because the expiration time is 10 seconds. And you can see it has returned 1. Let's load it again and let's remove the module after the timer has expired, which is timer is inactive in that case. The function is being called, timer handler function executed. Now the timer is inactive. Now let's remove the module. So delete underscore timer, it has returned 0. So there is one more function which is del underscore timer underscore sync. This function deactivates a timer and it waits for the handler to finish. The function only differs from del underscore timer and SMP. So the major difference is if you are having a UP, any processor machine, you can use del underscore timer. But if you are having an SMP, which is multiprocessor, symmetric multiprocessor, then you have to use del underscore timer underscore sync, delete underscore timer underscore sync. So this will guarantee that when it returns, the timer function is not running on any CPU. This is used to avoid race conditions on SMP systems. As timer, they run asynchronously with respect to the currently executing code, so causing race conditions. So this is the reason it has to be used on SMP. If it is a uniprocessor, you can use del underscore timer. But if it is a SMP, you have to use delete underscore timer underscore sync. So the same code in the exit function, instead of using del underscore timer, I'm using del underscore timer underscore sync. I'm loading this module. So the function is running. Let's remove the module and it returned 1. Let's again load it. The module is loaded. Let's wait until timer handler being executed. After it executes, yeah, it has executed. Now let's remove the module and it has returned 0. Same thing, it works like del underscore timer, but it is preferred to use, advised to use on SMP machines. So we have seen the one of the difference between del underscore timer and del underscore timer underscore sync is this will wait until, if the timer function is executing, suppose the timer handler is executing, and if you have called delete underscore timer underscore sync, this will wait until the timer handler completes, where this is not being achieved, performed by del underscore timer. Del underscore timer will not wait for the timer function to complete, whereas this will wait till sync, will wait until the timer handler completes. So I have added a delay here, like busy loop of 3 seconds. So what we'll do is we'll try to remove the module when we see this particular print statement. So I'm having a expiration time of 10 seconds. So I have scheduled timer to expire after 10 seconds, and let's remove this module when we see the first print k of the timer handler. So you can see it has written 0. You can see that there is a delay here, 378 and 382. So there is one more function which is timer underscore pending. This will tell whether a given timer is currently pending or not. If it is pending, it returns 1. If 0, if it is not. So the same code, which is setting the expiration time to 10 seconds. I'm calling timer underscore pending after setting the expiration time. What should be the value? It should be 0 or 1. It should be 1 because timer is still pending. I'm also calling this timer underscore pending from the timer handler. As the timer is already completed, it should return 0. So here it returned 1 because timer is pending. Now after the timer handler executes after 10 seconds, it returns 0 because timer is not pending. So this is this. How can I make this current timers periodic? Because these timers are only executing once. I have a scenario, I have a requirement where I want to periodically execute a particular function. I want to periodically check something is happening or not. So can I make the periodic timers? Can I use the kernel timers for periodic calling a function? Yes, you can make it by calling mod underscore timer in the timer handler. So if you modify the expiration time again in the timer handler, it will start executing it again. So again, what I'm doing is I'm calling mod underscore timer from the timer function. So I'm printing the expires and the jiffys here. Again, I'm printing the jiffys here after I'm calling mod underscore timer. So I can also add timer underscore pending here. So I can write verify timer pending returned. So timer underscore pending my timer. So here the timer is pending. Once I call mod underscore timer, we'll see what will be the value again. Should return 1. So the code here is again initial, it is setting the timer to expire after 10 seconds. Once the first timer expires and the timer function executes, it is again executing mod underscore timer, but now it is using jiffys plus milliseconds to jiffys. So it is setting this again timer function to execute after 1 second. And this will continue until you remove the module. So first expiration is after 10 seconds. So you can see it was pending 0, then it became 1. And now every 1 second you can see 605, 606, our timer function is being executed. So only way to stop this is to remove the module, which actually calls delete timer sync. Question for you. So how can I synchronize between process context and timer handler? Suppose if I want to share something, if I have some global structure, I want to synchronize between the process context as well as with the timer handler. How can I synchronize it? You can use spin locks because timer handler, it is running in interrupt context. You cannot use mutex or semaphores here. You have to use spin lock APIs. So I want to run the timer handler every 1 second. I think we have already seen this code. Not every 1 second. Yeah, every 1 second. I want to run the timer handler. I can use directly HZ, which is nothing but number of timer interrupts every second. So I can use milliseconds to GFEs of 1000. I can use HZ also, which will also give me the same behavior. So you can see now timer function is being executed every 1 second. Let's remove the module. Timer flags. Yeah, there are some flags which we can pass to timer. One of the flag is timer underscore deferrable. So using static initialization, you cannot pass any flags. You have to use dynamic initialization, which is timer underscore setup. It has an additional argument, which is flags. So one of the flags is timer underscore deferrable. So a deferrable timer will work normally when the system is busy. So it works as expected, but will not cause a CPU to come out of idle just to service it. So if you specify a flag as timer underscore deferrable, it will not cause the kernel to come out, CPU to come out of idle just to service it. The timer will be serviced only when the CPU eventually wakes up with a subsequent non-deferrable timer. So only when the non-deferrable timer expires, this particular timer will execute. So in case of dynamic ticks, CPU will not come out of idle. Like the timer interrupts are interval is variant, right? It is not periodic. So we can use this particular flags timer underscore deferrable to save the power consumption. So you can specify this if you want to save the power consumption. And if it is not a high priority task. So you cannot use define underscore timer here. You can have to use timer underscore setup. And now you can specify this flag timer underscore deferrable. It works same. In a busy system, it works same, but only when the CPU is idle. And when this particular timer expires, it does not bring this CPU back to normal just for executing this particular timer function. Only when a non-deferrable timer expires, this particular handler will be executed. So there is one more flag. There are a lot of flags where we are only discussing 2 flags. There is one more flag which is timer underscore IRQ safe. An IRQ safe timer, it is executed with IRQs disabled. So we have seen previously IRQs are enabled while running timer handler. But if you specify timer underscore IRQ safe, the particular timer is executed with IRQs disabled. So I'm using timer underscore setup. I have set the flag as timer underscore IRQ safe. And I'm having a 10-second of expiration time. And when the timer function executes, I'm checking whether the timer's IRQs are enabled or disabled. So let's run this code and verify it. So you can see here, this particular timer handler that is running with IRQ disabled. If you do not specify that flag, IRQs are enabled when the timer handler runs. So if you have any scenario where you want that IRQs to be disabled, you can use this particular flag. So one of the use cases of timers is schedule underscore timeout. We know schedule underscore timeout, it makes the current task sleep until timeout GFEs have elapsed. So schedule underscore timeout, it uses GFEs as an argument. So implementation of schedule underscore timeout is this particular file, kernel time timer.c. So we can go into kernel. Can you see scope schedule underscore timeout? So it uses timeout as an sign long, and depending on the timeout, suppose it is max schedule timeout, it just calls schedule. But if some other value is being passed, so max schedule timeout is just long underscore max. So max underscore schedule underscore timeout is long underscore max. So if you pass some other value, suppose if you pass a negative value, it just calls dump underscore stack. But if you pass some other value, then it sets the expire field, takes the timeout and adds it to the current GFEs. It has a structure which is process underscore time. So this process underscore time is having timer underscore list, which is our timer, and it is having a task struct for the current task, which is what it is having as a local variable here. So it sets the task to current, it creates a timer, and the flags are 0. It sets this is the it specifies this function to execute process underscore timeout, and it calls mod underscore timer with the expiry what we have specified. So now let's see, it calls schedule, and this particular process is scheduled. Let's go into this function process timeout. So once the particular timeout expires, timer expires, this function is being called, and this function gets back the structure process underscore timer from timer underscore list. So you can guess what is this particular thing, how it works. It is using container of to get the process underscore timer structure from timer underscore list. And it calls wake up underscore process. This is how that particular process is waken up. Very simple implement application of kernel timers. Schedule underscore timer internally uses kernel timers, and it schedules other tasks, and only after a particular time has expired, it wakes up the process. Very easy now to understand. So what is the problem with this particular timers? They work fine, right? What are the problems? The first problem is low resolution. So timers, kernel timers are only supported at a resolution of 1 GFE. So if you have GFE of like HZ value of 250, then you can have the resolution of 4 milliseconds. But you cannot have a resolution of 1 millisecond. You cannot have resolution of microsecond or nanosecond. So you have this particular timers, they have very low resolution. Multimedia applications, they need a resolution of microseconds or nanoseconds. They cannot, several milliseconds are not good enough for them because they need it for precise timekeeping, which is to avoid frame skips or jumps during video or audio playback. So this is the reason they cannot use low resolution timers. Hence, in 2.6 kernel, they have added high resolution timers, which is what we'll be discussing in our next session. So this is all about low resolution timer. Let's revise, let's have a quiz. Let's revise what we have discussed till now.